Greeting. Peace be with you. In this video, I am going to do an Arduino experiment using Raspberry Pi Pico on 28BYJ-48 step motor with ULN2003 board. DumbDisplay will be used as UI for controlling both the step motor's turn speed and angle. To rotate 28BYJ-48 step motor a full revolution, 4096 half steps are required. In this experiment, this half step is referred to as a sub-step. And in order to make the code easier to develop, 8 sub-steps are logically grouped as a turn step. An ULN2003 board will sit between the Raspberry Pi Pico and the step motor. One main purpose of the ULN2003 is to amplify the current from the Raspberry Pi Pico to be high enough to drive the step motor. Hence, the ULN2003 board is the driver of the step motor. Now, let's review the connection diagram. For the optional Bluetooth HC06 connections, connect BCC to BBus of Pico. Connect GND to a ground pin of Pico. Connect RXD to GP8 of Pico. Connect TXD to GP9 of Pico. For the connections between the Raspberry Pi Pico and ULN2003 board, connect in 1 to 4 to GP14 to 17 of Pico. Connect positive terminal to BBus of Pico. Connect negative terminal to a ground pin of Pico. Notice that the connection between the step motor and the ULN2003 board is a convenient connector cable. Now, let's review the sketch. Line 4 defines the macro, Bluetooth. In case connecting Bluetooth module like HC06 to connect to DumbDisplay Android app is not feasible at the moment, you can comment out line 4. If the macro, Bluetooth, is defined, lines 10 to 13 declare the DumbDisplay object, setting it to use Bluetooth connectivity with Raspberry Pi Pico's UART1. Notice that the baud rate set is 115,200. If the macro, Bluetooth, is not defined, lines 17 and 18 declare the DumbDisplay object, setting it to use USB serial as means of connection. In such a case, you will need the DumbDisplay Wi-Fi bridge to aid connecting to DumbDisplay Android app. Lines 25 to 28 define the pins connected to the ULN2003 board, the driver of the step motor. If no physical step motor is connected, comment out the pin defines. The DumbDisplay UI will still run without a physical step motor. Line 31 defines the maximum speed for the UI. Note that this speed is virtual, based on the maximum speed of the step motor. Line 33 defines the number of turn steps for the step motor to complete a revolution. It is a physical property of the step motor. Notice that 512 is 4096 divided by 8. In other words, to complete a revolution, 512 turn steps is required. Lines 38 to 46 declare the routine sub-step to trigger a half step of the step motor. To trigger a half step, a certain on-off pattern of the 4 driver input pins must be applied. Also notice the delay of 1 millisecond, which appears to be important for the sketch to work. Lines 48 to 68 declare the routine turn step, which make use to the routine sub-step to complete a turn step. For clockwise turn, line 50 to 57 call sub-step 8 times in succession, with some definite on-off pattern of the 4 driver input pins. For counter-clockwise turn, line 59 to 66 also call sub-step 8 times in succession, but this time, the on-off pattern is reversed. Lines 73 to 81 declare some constants for drawing of the step motor, rotor gauge on UI. Lines 85 to 93 declare the routine angle to XY, to find out where a point on the circle should be. The parameters to pass to the routine is the angle, and the radius of the circle. Conversely, line 94 to 109 declare the routine XY to angle, to find out the angle given a position. The parameters to pass to the routine is the X and Y coordinate of the position. Lines 111 to 118 declare the routine gauge angle to angle. It basically makes sure the angle parameter is in discrete 5-degree increment. Lines 123 to 126 declare the different DD layers for the UI. Calibrate layer, for the Calibrate tab. Control layer, for the Control tab. Turn speed layer, for the Turn speed meter. Gauge layer, for the step motor rotor gauge. Note that those layers will be created and set up in the setup block. Lines 130 to 151 declare the routine, draw motor pointer, to draw indicating dots on the gauge. 3 parameters are passed to the routine. At angle, is the angle where the step motor is considered at. To angle, is the angle to where the step motor should turn to. Turn on, is a flag indicating the pointer should be drawn, or erased. Yes, 2 dots will be drawn. One for indicating the angle the step motor is considered at, the other is the angle the step motor should turn to. Line 155 declares the global variable, motor at step, for storing the turn step count the step motor is considered at. Since a revolution has a fixed number of turn steps, the variable, motor at step, that is turn step count, basically indicates the angle of the step motor. Line 156 declares the global variable calibrated angle, for storing the step motor's angle at which it is considered calibrated. Line 158 declares the global variable at angle, for storing the angle the step motor is at. Notice that it is declared as the object type DD value record. As will be seen later on, this object is simply a convenient object to stage between new and known value. Similarly, line 159 declares the global variable to angle as the convenient object type DD value record. Apparently, this variable for storing the angle the step motor should turn to. Line 161 declares the global variable calibrating Boolean flag to indicate whether the current tab is calibrate or control. Line 162 declare the global variable turn speed for the speed of the step motor. Note that a speed of 0 means that the step motor should be stopped, a positive speed means that the step motor should turn clockwise, and a negative speed means that the step motor should turn counterclockwise. Line 164 declares the global variable DD connection checked for helping to check whether there has been a DumbDisplay reconnection, and therefore UI needs be refreshed forcefully. Line 167 starts declaring the DumbDisplay feedback handler, for handling different UI events. When the Control tab is clicked, line 169 simply sets the global variable calibrating to false. When the Calibrate tab is clicked, lines 171 to 173 set global variable calibrating to true, set turn speed to 0, and reset to angle to calibrated angle. When the turn speed meter is clicked, line 175 sets the global variable turn speed based on where on the turn speed meter was clicked. When the rotor gauge is clicked, lines 177 and 178 first find out the angle where on the rotor gauge was clicked. If it is calibrating, lines 180 to 185 perform the calibration by setting calibrated angle at angle and to angle to the clicked angle, and also by calculating and setting the global variable motor at step according to the angle. Notice that calibrating will only be done if the click was a double click. If it is not calibrating, line 187 simply sets the click angle to the global variable to angle, indicating which angle the step motor should turn to. Whatever layer is clicked, line 190 checks to see if it is not calibrating, that is using the gauge to control the step motor angle. Lines 191 to 196 set the global variable turn speed to its maximum value. Note that the turn speed may be flipped to negative to indicate that the step motor should turn counterclockwise. In the setup block, line 203 to 206 set the pin mode of the 4 driver input pins. Line 209 starts recording DumbDisplay commands, freezing the DumbDisplay screen, until the recorded commands are played back. Lines 211 to 214 create and set up the Calibrate layer, that is the Calibrate tab. Lines 216 to 219 create and set up the control layer, that is the control tab. Lines 221 to 224 create and set up the turn speed layer, that is the turn speed meter. Lines 226 and 227 create and set up the gauge layer, that is the rotor gauge. Lines 228 to 231 draw the four angles, 0, 90, 180 and 270, on the rotor gauge. Lines 232 to 237 print the angle indicating dots on the rotor gauge. Lines 239 to 243 instruct DumbDisplay to auto-pin the different layers in the desired way. At last of the setup block, line 245 play back the recorded commands, unfreezing the DumbDisplay screen. In the loop block, line 251 declare the local variable delay millis. This local variable is used to control how long to delay before looping. In other words, it controls the speed of the step motor. Lines 254 check the global variable turn speed is set to something. In such a case, lines 256 to 263 check whether the step motor should be turned. If the step motor should be turned, lines 265 and 266 turn the step motor according to the turn speed. If the turn speed is positive, it turns clockwise. If the turn speed is negative, it turns counterclockwise. Line 267 calculates how long to delay based on the turn speed, and set it to the local variable delay millis. Lines 369 to 273 calculate and synchronize the global variable motor at step of the step motor. Lines 274 and 275 calculate the corresponding at angle of the step motor. Line 280 checks the DD connection checker, to see if there was a reconnection, and assign the check result to the local variable force refresh UI. If force refresh UI, line 282 sets the rotor gauge background color. Lines 284 records the turn speed, global DD value record, object, and assigns whether recorded value changed from last value to the local variable turn speed changed. If turn speed changed, or force refresh UI, lines 386 to 330 turn on the turn speed meter, LEDs according to the turn speed. Line 302 records the calibrating, global DD value record, object, and assigns whether recorded value changed from last value to the local variable calibrating changed. If calibrating changed, or force refresh UI, lines 304 to 312 set the borders of the tabs, that is the calibrate, and control layers, according to whether it is now calibrating or not. Notice that if not calibrating, the turn speed meter will be made transparent. Lines 314 and 315 get the last at angle and last to angle. Lines 316 and 317 record the at angle and the to angle. If at angle changed, or to angle changed, or force refresh UI, lines 319 to 322 erase last pointer dots and redraw current pointer dots. Notice that the batch of commands to erase and redraw the dots are enclosed inside a record playback block so as to avoid flicking of the UI. At last of the loop block, lines 325 to 328 delays a certain amount of time according to the local variable delay millis. If the delay is positive, DD delay is called, otherwise, DD yield is called. That is it. Let's see the demo.